Definitions of Sobolev spaces and metric measure spaces is elegantly simple, and one can define all of them in a matter of one lecture. However, without some background in the Euclidean theory of Sobolev functions, one will have very little motivation, and one will have difficulty understanding the subtle choices that are made in developing such theory. So in this video, I decided to go over some basic properties of Euclidean Sobolev functions so that in future we can reference back to them and justify and explain why things are defined the way they are, and in what senses is one Sobolev function, one particular definition of Sobolev spaces different from the other one. One can go to Evans and Gariepy to pretty much have a summary of the Euclidean theory of Sobolev spaces. I also find the notes by Euclidean very useful, especially because he has some moral of the story paragraphs and summary paragraphs which nicely summarize the main points. Okay. So, in modern mathematics, we usually have detached ourselves from the formal definitions of objects and emphasized, on the other hand, what an object does. So, what a Sobolev function is one thing, but what are its properties and what does it do is actually the more significant thing. Once one gets into the details of advanced stuff in Sobolev theory, we notice that we don't really use that much what the definition of a weak partial derivative is really. It's just the properties and the axiomatic properties that we just combine together and manage to produce new proofs. So the definition of Sobolev functions W1P on open subset of Euclidean space definitely cannot be generalized into a metric setting at all. It needs the coordinates, the parallel fibration of Rn, and it needs the notion of compactly supported C infinity functions, none of which has any counterpart in abstract setting. But once we go beyond the definition, the properties begin to make sense. For example, we know that the W1P space is a Banach space. And that can definitely make sense on any metric measure space. All you need is a normed space that is complete under limits. This is a basic but yet very important property of Sobolev spaces, in fact, because the reason Sobolev spaces in Euclidean setting are so useful is because we turn PDE problems into variational problems where we're looking for minimizers. And how do you find a minimizer? Even in R1, how do you find the minimum of something? You just take a sequence of objects that produce and limit the minimum. And from that sequence, you hope to find a subsequence that converges. But if your space is not complete, that would-be limit will not live in your space, and that will be a failure. So being Banach space is important. When Nagios defined the Newtonian space, she also proved that certain definitions of Sobolev spaces do produce Banach spaces, which was an important result. The next thing is Sobolev embeddings. Sobolev, sometimes some versions are called Sobolev Poincare. So this is a spectrum of inequalities. What this says is that, for example, in the range less than n, bigger than 1, if you are in W1P of omega, then well, by definition, you are LP integrable, but what is more non-trivial is that actually you're better integrable your LP star, where this P star is np divided by n minus p, which you can confirm is always bigger than n. Actually, when p is pretty close to n, this is almost infinity. So the closer to n you get, better control you get on the function. For generic measurable functions, this is definitely not the case. That is why, for example, on the snowflake, where there are no rectifiable paths, the Newtonian space will produce just the LP, and that will not be interesting because, for example, you don't expect then any improved integrability for Sobolev functions, which is bad. And when P is strictly bigger than n, you actually get much stronger result that if you are in W1P of omega, then you are then U is almost everywhere equal to a function U tilde, which is actually a 1 minus n over p Holder continuous. And that makes sense in metric measure space. Being Holder continuous is just a metric property, so these are real values you can compare, and you just say that there's a constant c where CD, distance of xy to power alpha, bounds your oscillation of the function. Does this make sense? The question of whether a Sobolev function is Holder, is it a meaningful question? Is it a well-defined question in metric measure setting? Absolutely. So that's again a property that makes sense, just like being a Banach space. Another one is absolute continuity on a rectifiable path. If you restrict a Sobolev function on a rectifiable path in the space, so gamma is a path, that means it goes from a compact interval into your space X, and remember that U is a function from R to X to R, so U composed with gamma becomes a real valued function on a compact subinterval of real line. So this is just no ghosts here. It's not even quotation or anything. It's exactly a function from R to R, and absolute continuity is a very, very strong property for such functions. So where does this come from? It comes from a characterization of Sobolev functions in Rn, which says that, for example, for simplicity in R2, you take a domain. If you have a Sobolev function, then, for example, let's focus on lines parallel to x1. So you take a lot of lines parallel to 1, and every time you take a compact segment here, you can also remember that you can have exterior of this, so your omega doesn't have to be convex or anything. So when the line goes through that, it actually will produce two separate sections. So no middle here. Okay, so the result in the Euclidean setting is that if you have a Sobolev function, then for almost every line, which means forget a null set on this copy of R1, null being L1 Lebesgue measure, except for those lines, the rest will produce absolutely continuous functions on every segment within the line and the domain. This doesn't make sense in a metric measure setting because it relies on parallel lines to coordinate axis, but it turns out that you can get rid of this artificial reliance on Euclidean structure. It turns out that if you are a W1P function, then U composed with gamma is absolutely continuous for all gamma except, so if you take gammas that don't have to be parallel to anything, so on each one of them you will be absolutely continuous except for a certain collection of them. Except for a collection that has modulus 0. So mod p of that family of path will be 0. And modulus is something that can be defined on a metric measure space. So now this property will make sense even on a metric measure setting, because the notion of rectifiable path makes sense, the notion that this become continuous makes sense, and as I said, this also can easily be defined on a metric measure setting. Okay, so this is now another property of Sobolev functions that we can ask about. It's a valid question to say, is my Sobolev function on metric measure space absolutely continuous on almost every path? Dependence on p will be like p almost every path. That is the jargon used. And this notion is key to the definition of N1P space. Okay, and the next property is density of Lipschitz functions in the Sobolev space. We know actually in the Euclidean setting that even C infinity is dense, at least for nice domains. But C infinity doesn't make sense in metric measure settings, so already I make a sacrifice here. And this is a valid question. Is Lipschitz functions, which is a meaningful notion on a metric space, the question that are Lipschitz functions dense in certain Sobolev space, that question is valid and well-defined question. And finally, there is the question of fine properties, the term used in the title of Evans and Garipi's book. And by fine properties, we bring in the notion of capacity of sets, rather P capacity of set. So this is a notion that has been defined already in 96, 2 years after Hiwash's paper. This was defined in metric setting. And this is a way to capture smaller sets. Well, to be in the Euclidean setting, a function that is in the Sobolev space, from the beginning, it's only a measurable function, so you can change it on any set of Lebesgue measure 0, right? But we know that a Lebesgue measure that has a set that has Lebesgue measure 0 can nevertheless be very large. Its dimension can actually be n. What the fine properties say is basically that no, in reality, a function that is in W1P can exhibit arbitrary behavior only on a set E which has P capacity 0 or very small. And this in particular means that the dimension of the set is actually less than or equal to n minus p, which is much better than n. For example, if p is very close to n, say is n minus 1, this will be 1, which means that although you have a measurable function and it could change on a set as large as with dimension n, in reality, the Sobolev function really is restricted on any set that has dimension bigger than 1. So the function is free to behave wildly only on much smaller set, and that is what is referred to as fine properties. Another version of that is saying that if you give me an epsilon, there is a set which has capacity less than epsilon, p capacity less than epsilon, and then the function, when restricted to this domain minus this set, is continuous actually, which is what is called quasi-continuity of Sobolev functions. And again, this is a notion that does make sense to ask about in the general metric measure setting. So, several properties of Sobolev functions: that they are Banach spaces. I can also add here some weak compactness results, which again makes them perfect for variational methods. You have a sequence, you want to find a limit. What is better than having compactness and being complete? Okay, Sobolev inequalities, which give you better integrability than you start with. Absolute continuity on lines, very nice, very geometric, and definable on many settings. Density of Lipschitz functions and fine properties. So we see that all of these properties of Sobolev functions do have meaning in the general metric measure setting. What lacks a direct generalization is the definition. So we don't know what they are, but we know what to ask about them. And that's modern mathematics. And here is where we are. We have already hinted at definition of the Hajwas-Sobolev class, Poincare-Sobolev class defined by Hajwas and Koskela, a Cheeger class defined by Cheeger, the class N1P, the Newtonian class defined by Shamklingham, and the different inclusions between them. Also, again, I go back to one of the points that we don't want to find the best Sobolev space and forget the others, because, okay, this N1P contains this is a subset, but that doesn't mean this space is better. I just gave you the snowflake example where this just becomes all of LP. You don't have any Sobolev embedding. You don't have any absolute well, you have trivial absolute continuity of rectifiable path because there are no rectifiable path. So in that case, you may actually prefer this space because this is a smaller subset of LP in that case, and it may exhibit some of the nice properties that we have. So it's a question of what properties do you wish to have. So you have properties, and then depending on which ones you like, you want to have, which one is needed for your application that you have in your mind, then you decide which space to work with. And of course, there are many, many questions of for what spaces do you have equality between them? What is the role of Poincare inequality and whatnot? So that is the shortest crash course on Sobolev theory in Euclidean space that I've seen. But hopefully it gives you an idea of where we're standing, and hopefully it motivates you to go and check these properties out from the references that I mentioned, or even from Wikipedia or here and there. And to me, actually, having this already, this forward-looking vision that we're going to do stuff on metric measure spaces motivates you extra to learn this Euclidean theory better, because then you have a better chance of understanding what's happening, understanding the subtleties, formulating your own open questions, and hopefully investigating one of them and producing new math that gets published. Okay, until then, not until then, but until next video, have a great one, and bye-bye.